When a switch is closed, battery voltage is suddenly applied to an RL circuit. Initially, the inductor acts as a short circuit because of its zero initial current, while the resistor limits the current. As a result, nearly all the voltage drops across the resistor, with minimal current flowing through the inductor. Over time, the inductor gradually builds up current, increasing its magnetic field. This process opposes the change in current, causing the voltage across the inductor to decrease. As the inductor stores more energy, less current flows through the resistor, leading to a decrease in its voltage drop. Eventually, in steady state, at infinity, the inductor fully stores the battery voltage and acts as an open circuit. The current through the inductor reaches its maximum, while the current through the resistor becomes zero. Almost all the voltage now drops across the inductor. Now let's examine the mathematical explanation. At time equals 0 plus, immediately after closing the switch, Kirchhoff's voltage law states that the voltage equals the current times resistance. The current through the inductor equals 0 amps. The voltage across the resistor equals 0 volts. The voltage across the inductor equals the source voltage. At time equals infinity, that is at steady state, Kirchhoff's voltage law states that the voltage equals the current times the resistance plus the inductance times the change in current with respect to time. The current through the inductor equals the voltage divided by the resistance. The voltage across the resistor equals 0 volts. The voltage across the inductor equals the applied voltage. The rate of current build-up through the inductor is determined by the time constant tau, which equals inductance divided by resistance. The voltage across the resistor decays exponentially over time with a time constant tau. The voltage across the inductor increases exponentially over time with a time constant tau. In more detail, let's discuss the behavior of an RL circuit when a step voltage is applied. The fundamental equation governing this circuit is derived from Kirchhoff's voltage law, which states that the sum of voltages around any closed loop must equal 0. In an RL circuit connected to a voltage source, this translates to the source voltage, let's call it V, being equal to the sum of the voltage drop across the resistor and the voltage drop across the inductor. Mathematically, this is expressed as V equals I times R plus L times d over dt, where I is the current flowing through the circuit, R is the resistance, L is the inductance, and d over dt represents the rate of change of current with respect to time. This is a first-order differential equation, and its solution describes how the current changes over time. When the switch is first closed at time equals 0, the inductor opposes any immediate change in current. Therefore, the current starts at 0. As time progresses, the current begins to increase, but its rate of increase is limited by the inductor. The inductor stores energy in its magnetic field, and the voltage across the inductor is proportional to the rate of change of current. The resistor, on the other hand, obeys Ohm's law, where the voltage across the resistor is simply the product of the current and the resistance. The time constant, tau, which equals L over R, plays a crucial role in determining the speed at which the current approaches its final steady-state value. A larger time constant indicates a slower response, while a smaller time constant means a faster response. Now let's look at the step-by-step analysis. Firstly, at time t equals 0, immediately after the switch is closed, the current is 0 because the inductor opposes instantaneous changes in current. The inductor acts as an open circuit momentarily. As a result, the entire voltage source V appears across the inductor. The voltage across the resistor is 0 since there is no current flowing through it. Secondly, as time increases from 0, the current begins to increase. As the current increases, the voltage across the resistor also increases according to Ohm's law. However, the voltage across the inductor decreases because the rate of change of current is decreasing. The inductor is gradually allowing more current to flow. Thirdly, at steady state, as time approaches infinity, the current reaches its maximum value, which is V divided by R. At this point, the inductor acts as a short circuit because the current is no longer changing. As a result, the voltage across the inductor is 0, and the entire voltage source appears across the resistor. The current through the inductor is constant and equal to V over R. The voltage across the resistor is V, and the voltage across the inductor is 0 volts. To further understand the transient behavior, we can solve the differential equation. The solution for the current as a function of time is given by I of t equals v over r times 1 minus e to the power of negative t over tau. This equation shows that the current starts at 0 and exponentially approaches the steady state value v over r. The voltage across the resistor as a function of time is given by v sub r of t equals I of t times r, which simplifies to v times 1 minus e to the power of negative t over tau. This equation shows that the voltage across the resistor starts at 0 and exponentially approaches the source voltage, V. The voltage across the inductor as a function of time is given by V sub L of t equals L times d over dt, which simplifies to V times e to the power of negative t over tau. This equation shows that the voltage across the inductor starts at V and exponentially decays to 0. These equations provide a complete picture of the transient response of an RL circuit to a step voltage. They allow us to calculate the current and voltages at any point in time, given the values of V, R, and L. In summary, the behavior of an RL circuit when a step voltage is applied is characterized by the inductor opposing changes in current and the resistor obeying Ohm's law. The time constant tau, which equals L over R, determines the speed at which the circuit reaches steady state. The current starts at 0 and exponentially approaches V over R. The voltage across the resistor starts at 0 and exponentially approaches V, and the voltage across the inductor starts at V and exponentially decays to 0. Let's delve deeper into the mathematics behind the RL circuit step response. The governing differential equation, V equals IR plus LD slash dt, can be rearranged to solve for d slash dt, giving us d slash dt equals V minus IR divided by L. This equation tells us how the rate of change of current depends on the source voltage, the current itself, the resistance, and the inductance. To solve this differential equation, we can use separation of variables. We rewrite the equation as d divided by V minus IR equals dt divided by L. Integrating both sides, we get the integral of t divided by V minus IR equals the integral of dt divided by L. The left-hand side integrates to negative 1 over r times the natural logarithm of the absolute value of V minus IR, and the right-hand side integrates to t divided by L plus a constant of integration c. Solving for I, we first multiply both sides by negative r, giving us the natural logarithm of the absolute value of V minus IR equals negative RT over L plus negative RC. Exponentiating both sides, we get the absolute value of V minus IR equals e to the power of negative RT over L plus negative RC, which can be rewritten as e to the power of negative RT over L times e to the power of negative RC. Let e equals plus or minus e to the power of negative RC, where the plus or minus sign accounts for the absolute value. Then we have V minus IR equals e to the power of negative RT over L. Solving for I, we get IR equals V minus e to the power of negative RT over L, and finally, I equals V over R minus over R times e to the power of negative RT over L. To determine the constant A, we use the initial condition that I equals 0 at t equals 0. Substituting these values into the equation for I, we get 0 equals V over R minus over R times e to the power of 0, which simplifies to 0 equals V over R minus over R. Solving for R, we get E equals V. Substituting E equals V back into the equation for I, we get I of t equals V over R minus V over R times e to the power of negative RT over L, which simplifies to I of t equals V over R times 1 minus e to the power of negative RT over L. This is the same equation we derived earlier, which confirms our solution. Now let's consider the voltage across the inductor, V sub L. We know that V sub L equals LT slash dt. Taking the derivative of I of t with respect to t, we get d slash dt equals V over R times the derivative of 1 minus e to the power of negative RT over L. The derivative of 1 is 0, and the derivative of negative e to the power of negative RT over L is R over L times e to the power of negative RT over L. Therefore, d slash dt equals V over R times R over L times e to the power of negative RT over L, which simplifies to d/dt equals v over L times e to the power of negative RT over L. Substituting this into the equation for v sub L, we get v sub L of t equals L times v over L times e to the power of negative RT over L, which simplifies to v sub L of t equals v times e to the power of negative RT over L. This is also the same equation we derived earlier, which further confirms our solution. To summarize, we have derived the equations for the current and the voltage across the inductor in an RL circuit when a step voltage is applied. These equations are I of t equals v over R times 1 minus e to the power of negative RT over L, and v sub L of t equals v times e to the power of negative RT over L. These equations are fundamental to understanding the transient behavior of RL circuits. Let's now discuss the energy stored in the inductor. The energy stored in an inductor is given by the equation E equals 1/2 times L times I squared, where E is the energy in joules, L is the inductance in henries, and I is the current in amps. As the current in the RL circuit increases, the energy stored in the inductor also increases. At time equals 0, the current is 0, so the energy stored in the inductor is also 0. As time approaches infinity, the current approaches V over R, so the energy stored in the inductor approaches 1/2 times L times V over R squared, which simplifies to 1/2 times L times V squared divided by R squared. The rate at which energy is stored in the inductor is given by the derivative of the energy with respect to time. Taking the derivative of E equals 1/2 times L times I squared with respect to time, we get d/dt equals L times I times d/dt. Substituting the equations for I and d/dt that we derived earlier, we get d/dt equals L times V over R times 1 minus e to the power of negative RT over L times V over L times e to the power of negative RT over L, which simplifies to d/dt equals v squared over R times 1 minus e to the power of negative RT over L times e to the power of negative RT over L. This equation shows that the rate at which energy is stored in the inductor is initially high and then decreases as time approaches infinity. The total energy stored in the inductor is equal to the integral of the rate of energy storage with respect to time from time equals 0 to time equals infinity. Integrating the equation for d/dt, we get E equals the integral from 0 to infinity of v squared over R times 1 minus e to the power of negative RT over L times e to the power of negative RT over L dt. This integral can be evaluated to show that the total energy stored in the inductor is indeed 1/2 times L times v squared divided by R squared, as we found earlier. In addition to the energy stored in the inductor, there is also energy dissipated in the resistor. The power dissipated in the resistor is given by the equation P equals I squared times R, where P is the power in watts, I is the current in amps, and R is the resistance in ohms. Substituting the equation for I that we derived earlier, we get P of T equals V over R times 1 minus e to the power of negative RT over L squared times R, which simplifies to P of T equals V squared over R times 1 minus e to the power of negative RT over L squared. The total energy dissipated in the resistor is equal to the integral of the power with respect to time from time equals 0 to time equals infinity. Integrating the equation for P of T, we get E equals the integral from 0 to infinity of V squared over R times 1 minus e to the power of negative RT over L squared dt. This integral can be evaluated to show that the total energy dissipated in the resistor is equal to 1/2 times L times V squared divided by R squared, which is the same as the total energy stored in the inductor. This result shows that all of the energy supplied by the voltage source is either stored in the inductor or dissipated in the resistor. No energy is lost in the circuit. Let's discuss the concept of impedance in RL circuits. Impedance is the total opposition to current flow in an AC circuit, and it includes both resistance and reactance. In an RL circuit, the impedance C is a complex quantity given by Z equals R plus J omega L, where R is the resistance, J is the imaginary unit, omega is the angular frequency of the AC source, and L is the inductance. The magnitude of the impedance is given by the square root of R squared plus omega squared L squared. The phase angle of the impedance is given by the arctangent of omega L divided by R. When a step voltage is applied to an RL circuit, we can think of it as an AC signal with an angular frequency of 0. In this case, the impedance simplifies to Z equals R plus J times 0 times L, which simplifies to Z equals R. This means that at time equals 0, the impedance of the RL circuit is simply equal to the resistance. As time approaches infinity, the frequency approaches 0, and the impedance remains equal to the resistance. However, during the transient period, the frequency is not 0, and the impedance is a complex quantity that varies with time. The transient behavior of the RL circuit can be analyzed using Laplace transforms. The Laplace transform of the voltage source is V over S, where S is the complex frequency variable. The Laplace transform of the current is I of S equals V over S divided by Z of S, where Z of S is the impedance of the RL circuit in the S domain. The impedance in the S domain is given by Z of S equals R plus SL. Therefore, the Laplace transform of the current is I of S equals V over S divided by R plus SL, which can be rewritten as I of S equals V divided by S times R plus SL. To find the time domain current, we need to take the inverse Laplace transform of I of S. Using partial fraction expansion, we can write I of S as I of S equals V over R times 1 over S minus 1 over S plus R over L. Taking the inverse Laplace transform, we get I of t equals V over R times 1 minus e to the power of negative RT over L, which is the same equation we derived earlier. This confirms that the Laplace transform method gives the same result as the time domain method. Let's also discuss the duality between RL and RC circuits. An RL circuit consists of a resistor and an inductor connected in series or parallel, while an RC circuit consists of a resistor and a capacitor connected in series or parallel. The behavior of RL and RC circuits is governed by similar differential equations, but with the roles of voltage and current interchanged. For example, in an RL circuit, the current increases exponentially when a step voltage is applied, while in an RC circuit, the voltage increases exponentially when a step current is applied. The time constant for an RL circuit is L over R, while the time constant for an RC circuit is RC. The frequency response of an RL circuit is the inverse of the frequency response of an RC circuit. For example, an RL circuit acts as a high-pass filter, while an RC circuit acts as a low-pass filter. The duality between RL and RC circuits can be used to simplify circuit analysis and design. For example, if we know the behavior of an RC circuit, we can use duality to determine the behavior of an RL circuit, and vice versa.